Suppose that we start with an equilateral triangle. As you recall, an equilateral triangle has three angles, all of which are 60 degrees. Now let's suppose that we take this equilateral triangle and rotate it counterclockwise by 120 degrees. So what we're going to do is we're going to do a rotation in this direction by 120 degrees. And we're interested in what will the triangle look like if we do this rotation on the triangle. And what we'll get is we'll get a triangle that looks like this. In other words, the triangle will look exactly the same as it did before if we do this 120 degree rotation on the triangle. For contrast, let's take this triangle, again an equilateral triangle, and rotate it counterclockwise. But this time, let's rotate it by 60 degrees. So if we do a 60 degree rotation on our equilateral triangle, what will it look like? Well, notice that we end up getting a triangle that looks like this. Okay? And we notice that it looks different. Our original triangle, it had the vertex pointing straight up. After we rotated it by 120 degrees, again, we have an equilateral triangle pointing up. But if we rotate it counterclockwise by 60 degrees, we notice now that it has a vertex pointing down. So we notice that it looks different. What we are going to be most interested in inorganic chemistry are the motions that we can do on a shape that make it look the same as it started. Okay, so we notice that for a triangle, an equilateral triangle, if we rotate it by 120 degrees, it looks the same. If we rotate it by 60 degrees, it doesn't look the same. So the motions that make it look the same, we're interested in those. Those are the ones that are going to be important. Now this rotation by 120 degrees, we use a special symbol for it. We call it a C3 rotation. Okay? The C is for cyclic. It's a rotation, and we're going to call it a special type of rotation, a proper rotation. The 3 can be thought of several different ways. One of the ways is if I rotate by 120 degrees, I rotate it by 1/3 of a full circle. That's one way to do it. Another way, a more general way to write, is to notice that if I have a rotation that's a Cn rotation, so n will be a whole number, it will be an integer, the rotation will be by 360 degrees divided by n. So in the case where n is equal to 3, we notice that we have a rotation of 120 degrees. We can say that the equilateral triangle has a C3 symmetry operation. Symmetry operations of a shape will be those motions that we do on the shape, which makes it look exactly the same as it did before. Now, let's take our equilateral triangle that we started with its vertex pointing straight up, so we can keep track of where it is. And this time, let's rotate it by 240 degrees. So let's rotate in a counterclockwise direction, 240 degrees. Well, one of the things that we would recognize is that I can break this 240 degrees up into two individual rotations. I can rotate it once by 120 degrees, in which case it looks the same as it did before. And then I can rotate this shape 120 degrees, and I get this shape. And I realize after having rotated the equilateral triangle by 240 degrees, it looks exactly the same as it did before. Therefore, this 240 degree rotation is a symmetry operation of the equilateral triangle. The way that we can write this is we can think of it as 220-degree rotations done in a sequence. So we can think of it as a C3 rotation followed by another C3 rotation. And for mathematical reasons, we tend to go from right to left with our operations. And when we do two operations in a row, for reasons which will become clear later on, we can think of this as almost a multiplication. Okay, so if I do two operations, I can think of them as being multiplied together in a certain sort of way. So because of this, when we have a C3 followed by another C3 operation, we can think of the total effect of this as C3 squared. So we can almost use the rules of exponents to combine these two operations into a single operation. So this is the way that we have to write a rotation by 240 degrees. When we use the Cn notation, n has to be a whole number. It has to be an integer. So we can write it this way. We have Cn, where n is an element of the integers. So the integer, the fancy way to write that is a stylized capital Z, and that tells us that we have an integer. In summary, we've seen two symmetry operations for the equilateral triangle. We see that it has C3, and it also has C3 squared. We can also think of it intuitively as taking our triangle, moving it a third of a turn with one C3, and a second turn to the left by another 120 degrees. Now, one thing we might notice is that we could achieve the same effect, have this vertex here that we started with, after one C3 goes to here, after the second C3 goes to this vertex. I could have achieved the same result by rotating 120 degrees in the clockwise direction. So our 240-degree rotation counterclockwise is equivalent to a rotation clockwise. So you get the same effect by a 120-degree rotation clockwise. And again, since our C rotations are done in terms of being counterclockwise, how can we write that as a symbol? Well, the symbol that we use in the case of counterclockwise operation, it's like a C3 operation, but in the opposite direction. And again, for mathematical reasons which will become clearer later on, we can write this as C3 to the minus 1. So we're using some abusive notation to start off with, but we're going to see later on that we have good mathematical reasons for this particular notation that we're using. So in summary so far, we've seen that for the equilateral triangle, it has a C3 symmetry operation, it has a C3 squared symmetry operation, and it has a C3 to the minus 1 operation. We would like to see if the equilateral triangle has any other proper rotations. Well, one operation, which may not seem obvious at first, is that we can take our equilateral triangle and rotate it now by 360 degrees. And if I take an equilateral triangle and rotate it one whole complete turn, 360 degrees, I'll notice that it will look exactly the same as it did before. We're left with our equilateral triangle. So I notice that a rotation by 360 degrees is a symmetry operation of the equilateral triangle. And in fact, if I take any shape at all, and rotate it by 360 degrees, I get the exact same shape back. So any object you could ever want to name has this 360-degree rotation as a symmetry operation. There are several different ways that we denote this particular symmetry operation. One way is to note it as C1 because it's 360 degrees divided by 1 equals 360. We think of 1 as one whole turn, one whole part of a turn. So you'll see it written as C1, but it's also written in a slightly different way. It's given its own special symbol, the letter E. In this case, the letter E is short for the German word Einheit, which is identity. And the reason why we call it the identity will become clear later on, but for the time being, we can recognize is that if we take any object and we rotate it by 360 degrees, it looks as if we have not rotated it at all. So any object, no matter what, will have this C1 operation. You may think, therefore, that it's trivial, that's not important. And in many ways, E is the Rodney Dangerfield of symmetry operations, but for mathematical reasons, which become critical later on, this is an essential part of our mathematical description of symmetry. Now, let's take a different shape, the square. And we recall that in a square, all four angles are the same. They're 90 degrees. They are our right angle. And all four sides of the rectangle are the same length. So that is a geometric way of describing a square. But we can also describe a square in terms of symmetry operations. For example, if we take the square and I rotate it counterclockwise by 90 degrees, I would realize that if I rotate it this way, I end up getting a shape that looks the same. If I rotate it by 90 degrees without you watching me, and you came back and looked at the shape, you would not recognize that it had been moved. And that's a good sign of a symmetry operation. So in this case, because it's a quarter of a turn, it's 90 degrees, we refer to this 90-degree rotation as a C4. So one of the ways of defining a square is a geometric object for which C4 is a symmetry operation. Now we also notice that if we take a square, we can rotate it by 180 degrees. So, for example, 180 degrees would rotate from here to there. So it would be a half of a turn. This is 180 degrees. So we can define, in terms of proper rotations, this 180 degree rotation is a C2. It's C2 because it's a half of a full turn. That's an intuitive way of thinking about it. Also, using our formula, that 360 divided by 2 is 180 degrees, and we've rotated by 180 degrees. Now, one thing you may notice is you may think, well, when I rotated 180 degrees, could I have first rotated it by 90 and then rotated another 90 degrees? Sort of do a two-step process. And yes, you could have. So what it tells us is that if I do two C4s in a row, I get a C2. So one way to write this mathematically is C4 times C4 equals C2, if we're talking about a square. So we notice that a square has a C4 operation and a C2 operation. But it also has other rotations available. So for example, let's go back up here, but now let's say instead of rotating it in the counterclockwise direction, I decide I'm going to rotate it in the clockwise direction. So our clockwise rotation would go in this direction. So if I go 90 degrees in this direction, recall that one of the ways that we can define such a rotation is by using an exponent, and an exponent in the opposite direction is -1. So a rotation clockwise by 90 degrees is denoted as C4 to the -1. So for a square, we notice what symmetry operations does it have. We notice it has C4 going 90 degrees counterclockwise. It has C4 -1, so it goes 90 degrees clockwise. it has a C2 operation, so it's going counterclockwise by 180 degrees. Does it have any other ones? Well, it always has E, so every shape has E, which recall is the same thing as C1. Now you may wonder, can we do the same trick that we did here by rotating clockwise with a C2? Well, we can, but notice that if we rotate by 180 degrees clockwise, we get to exactly the same position that we would have gotten by rotating 180 degrees counterclockwise. So effectively, C2 and C2 to the minus 1 are going to be equal in this case. So in cases where they'd be equal, we simply don't write it this way. So we just leave it as C2. So we see that a symmetrical way of describing differences between an equilateral triangle and a square is in terms of an equilateral triangle has a C3 squared, and E symmetry operations, whereas a square has C4 to the minus 1, C2, and E proper rotations as symmetry operations. This idea of defining geometric shapes in terms of the motions that we do on them to make them look the same is from the early 20th century, from the great German mathematician Felix Klein. So Felix Klein redefined geometry in terms of these motions of geometric objects. Another geometric shape that you might recall from high school is the rectangle. And here we've taken a rectangle that is not a square, so we have a short width and a longer length. And to make our demonstration clearer, we've displayed our rectangle in a so-called landscape orientation. So as if you're doing a picture of a landscape and it's longer horizontally than it is vertically. So we want to look at what symmetry operations are available from the rectangle. Well, one we might recognize right away is that if I rotate by 180 degrees, it will look the same as it did before. So if I rotate it by 180 degrees, what will my rectangle look like? It'll look like this. It will still be in the landscape orientation. So that tells us that it has the following symmetry operation. It has a C2. So just like the square, we notice that a rectangle has a C2 proper rotation. But now let's look at something that we saw from the square, was that with a square we could do a rotation by 90 degrees. Let's see what happens if I decide to rotate by 90 degrees for my rectangle. Well, what will our rectangle look like if I rotate it by 90 degrees? Well, it'll look like this. Now my rectangle is in a so-called portrait orientation. And I can tell immediately it doesn't look the same as it did before. I can tell that I started with a rectangle that was in the landscape orientation, and after doing a 90-degree rotation, I clearly have a portrait. What does this tell me? It tells me that a rectangle, at least a generic rectangle, does not have a C4 symmetry operation. So this provides another way to distinguish between rectangles and squares. So we know, for example, from high school geometry, that a square is a special case of a rectangle where all four sides are the same. In a more sophisticated symmetrical analysis, we can say that a square has a C4 and a C2 symmetry operation, whereas a rectangle has only the C2. And recall, it has things like the E operation, which every single shape has. We don't want to leave that out, but that's going to be present for every single shape that we have. So we can see more clearly with the rectangle that it doesn't have the C4 operation.